Welcome to the second class on knowledge representation. This video lecture will cover the Russell and Norvig text, chapter 12.4 to 12.6. In my last video, I covered the first part of the chapter, and in particular, I covered ontological engineering, categories and objects, and actions, situations, and events. In this video, I'm going to cover mental events and mental objects, reasoning systems for categories, reasoning with default information, and truth maintenance systems. I'm really going to be covering the highlights of the chapter, the things that I really want you to know. The chapter is full of a lot of other information, all valuable. And so this is sort of a best of tour in a way. Well, let's start with mental events and objects. Up to now, when we represent a fact, it's something that's true, like the car is red. When you introduce agents who can have their own independent beliefs, then you end up with a much more complicated but more powerful approach to logic. So let's start from the standpoint that knowledge-based agents can have beliefs and they can deduce new beliefs from what they know and what they can observe. This is called epistemic logic. Epistemic means of or relating to knowledge or knowing. It's just a fancy word that means we're going to be reasoning about knowledge or knowing. Now, in epistemic logic and reasoning with knowledge and beliefs, there are a number of propositional attitudes that an agent can have towards mental objects. In other words, towards things that it knows or believes. So those propositional attitudes, which we can represent as predicates, include believes, knows, wants, intends, informs, and so forth. So things like believe and know relate to the state of the agent's beliefs or knowledge about the world. Wants and intends relate to the agent's goals, and informs relates to actions taken in the world. And in a later lecture, when we work together on speech acts, we'll learn a lot more about this kind of action. This is the point, though, where we have to talk about referential transparency and opacity. Referential transparency is being able to substitute referentially equivalent expressions. For example, I saw a coyote on my street, and I saw a coyote on Mira Hermosa Drive mean the same thing, as we can substitute Mira Hermosa Drive for my street. But referential transparency causes problems for epistemic logic. If Bruce Wayne is Batman, and if Commissioner Gordon knows that Bruce Wayne is wealthy, it's probably not true that Commissioner Gordon knows that Batman is wealthy. Similarly, if Luke Skywalker knows about Darth Vader, and it's also true that Darth Vader is Luke Skywalker's father, it may not be the case that Luke knows his own father. This poses serious problems. So instead of referential transparency, modal logic relies on referential opacity. That is, we can't substitute referentially equivalent expressions. Let's turn now to modal logic. Modal logic includes special modal operators that take sentences rather than terms as arguments. So A knows P. That is, the agent A knows some proposition P, where P could be something like Darth Vader is Luke's father. We represent that more formally in the logic as knows, that's the capital K there, sub A, that's the agent, the proposition P. Or in a prologue representation would be knows, agent, proposition. The reason we have modal logic is that an agent's belief doesn't have to be true. My grandmother sincerely thought that islands floated, yet it's true that she had this belief, and her belief is true in one of many possible worlds that we could specify. Our work, though, is to be clear which worlds are accessible from which worlds so that contradictions and untrue situations do not arise. We say that world W1 is accessible from world W0 with respect to the modal operator K sub A if everything in W1 is consistent with what A knows in W0. And we can represent this in predicate form, saying that something is accessible to the modal operator K sub A from world 0 to world 1. A lot of artificial intelligence involves reasoning about categories and instances of categories. You're familiar with these because you've already had to work with object-oriented programming, so you understand the difference between classes and instances, and you know how inheritance works. So here, instead of working with modules and bits of code, we're thinking about organizing and reasoning with categories and instances in the real world, or the world of the intelligent agent. Semantic networks form an important part of this. They enable us to visualize the knowledge base, and we'll look at an example of a semantic network in just a minute. And the good news is that semantic networks provide efficient algorithms for making inferences about category membership. Associated with semantic networks are description logics. Now, these are formal languages for constructing and combining category definitions. So it's not just a picture, it's an actual representation in a language that a computer might understand. And it provides an efficient algorithm to decide subset and superset relationships between categories. So here's an example of a semantic network from the text, and I want to point out a couple of things about this. First, we can see that some of the elements in the semantic network are categories and some are instances. So, for instance, mammals, persons, female persons, and male persons are all categories of things, whereas Mary and John are instances. And we can see that because the relationship between Mary and female persons, for example, is member of. Not all relationships are member relationships, though. So we know that female persons, for instance, are a subset of persons. It's also true that every person has a mother. If we take a look at the relation has mother, which is a binary relation between persons and female persons, there's some important things to notice. First, it's not true that the category persons has a mother. Rather, it's instances of the category person that has the mother. Mary has a mother, John has a mother, and so forth. Also, it's not true that the thing that has mother is pointing to, the category female persons, is what constitutes a mother. Rather, what's true is that the person, the element that's a mother, is a member of the category female persons. So that's why has mother has a double box around it. It's a relationship between instances of the category persons and instances of the category female persons. Another similar issue arises with the relationship legs. So it's true that all people have legs, but that's true of the instances of the category persons, not the category persons itself. Now, the object of the relation is going to be a number, like 2, for instance, and so we just have a single box around there because it's not a relationship between instances of the category, whatever legs points to. It's just the number 2. A little more about semantic networks. There are lots of variations and representations, but all represent individual objects, categories of objects, and relationships among objects. And the good news about this is that it enables us to reason about inheritance. For instance, female persons inherit all the properties from person. Now, you can reason in both directions, right? So that we can reason in both directions, so that sister of is the inverse of has sister, and you'd want to represent both of those links. Now, there are some drawbacks with semantic networks. The links can only assert binary relationships. In other words, Mary is an instance of person, or males are people. Now, we can resolve this problem about links only asserting binary relationships with reification of the proposition as an event. Reification means turning a relationship into a thing. Re comes from the Latin word res, or thing. In other words, it's the thingification. If we have a relationship, maybe binary, maybe n-ary, to which we need to refer, we can simply classify that particular relationship between those particular objects as a thing in and of itself. For example, student Josie, senior UTEP, which I take to mean that Josie is a senior at UTEP, can be the argument, when reified, of a modal operator such as believe, such as that Gary believes that Josie is a senior at UTEP. Another nice element of semantic networks is that they enable us to represent default values. So, for instance, all people have 2 legs, and so I don't have to represent that men have 2 legs and women have 2 legs. They can inherit it from the category person. Description logics enable us to represent semantic networks, these definitions and properties of categories, in a way that's formal. And there are 3 principal kinds of inference we need to do. The first is subsumption, which is checking if one category is the subset of another by comparing their definitions. For example, a category student could inherit from human, in which case human subsumes student. The second task is classification. That's checking to see whether an object belongs to a category. And that's pretty easy because you can just see if it's an instance of a category or if the category it belongs to is subsumed by another category. And then there's consistency. And that's checking whether the category membership criteria are logically satisfiable. Does Josie meet all the criteria for being a student, for instance? Description logics enable us to reason with default information. So, for instance, if I have a statement like, the following courses are offered: CS 1401, CS 2401, CS 4390, and Engineering 4320, how many courses are there? Well, if we have a representation that's a database, then we would say there are 4. In this approach, we assume that the information is complete. That is, that anything that's not asserted as a fact is false. And that's what's called the closed world assumption. The other assumption in this database approach is that distinct names refer to distinct objects. That's the unique names assumption. In other words, CS1401, CS2401, CS4390, and ENG4320 are all distinct courses. Now, that might not be true. For instance, next semester, I'll be teaching a class that will be cross-listed as a 4390 and an ENGR 4320. So in a more purely logical representation, not just as a database, we don't make these assumptions. That is, the closed world assumption isn't true. There might be other courses beyond these four, or maybe there are some of these courses are the same course. There could be between 1 and infinity number of courses. Also, this requires completion. And this is discussed back in chapter 9.4, but there's a way of showing or representing using logical expressions that, in fact, these are the only 4 courses, if that is what we want to represent. Finally, I want to talk a little bit about truth maintenance systems. Some of the inferences we can do have default status rather than being absolutely certain. For instance, in our representation of person, we said that they have 2 legs. Well, some people don't have 2 legs. So inferred facts can be wrong and need to be retracted. That's called belief revision. And so we can assume that a knowledge base contains sentence P, and we want to tell the knowledge base not P is true. So to avoid a contradiction, we need to retract P from the knowledge base. But what about all those sentences inferred from P? Well, that goes back to the frame problem that you read about in chapter 7.7. And to deal with this problem, there are what are called truth maintenance systems. And these are systems that keep track of what was deduced from what and what depends on what, so that if something is retracted, those conclusions, those implications are also retracted. So this completes our brief tour of representation issues, and I look forward to seeing you in class.